A very good morning to one and all. Let us continue with the discussion on the remaining useful modeling techniques, the time scale. So, what is the time scale? It is a compiler directive. Whenever we are writing any program in our Verilog HDL, we can find this time scale before your main module. So, what is the purpose of the time scale and what is its importance in our Verilog program? We will discuss. So, sometimes a test bench program or a design program definitely contains or associates with some delays or delay value. That means a delay value in a module need to be defined by using certain time unit. For example, I am writing some Verilog program here. #5 assign A equal to B and C. That means here #5 is there. I don't know what is the basic time unit for 5, like whether it is a seconds or like minutes or nanoseconds or picoseconds or whatever it is. I am unaware of that thing. So in order to know what exactly the time unit for, like how much amount of delay it is taking in practical, the timescale compiler directive is highly helpful. So here in the Verilog HDL, it allows the reference time unit or a basic time unit for the modules or the for test bench program to be specified by using we call this is a backtick. So backtick timescale compiler directive, and the syntax we follow here is backtick timescale reference time unit oblique time precision. We do have in this manner. Okay, so what is this reference time unit and what is the time precision here? So the reference time unit generally specifies the unit of measurement for the time or delay. And coming to the time precision, it generally specifies the precision to which the delays are rounded off during the time of simulation. Like for example, you can see here the reference time unit for a module, it should be in the form of 1, 10, 100 picoseconds, nanoseconds, micro or milli or seconds. So, and the precision specifies the precision to which the delays are rounded off. For example, here you can see 1 second by 1 millisecond we are having here. That means that means what is the delay? Like for example, the accurate value of the time unit is 1 second and the precise value of your time unit is 1.001 second, we can say. So before knowing about in brief about the time scales, we should know certain terminologies like accuracy and precision. In our mathematics, we do have a symbol called pi, and the value of pi is generally 3.14. So what is the accurate value of a pi? We can say it as 3.14, and what is the precise value of a pi? It is 3.131984 and so on. That means here precision and accuracy, what does it conveys us? A precision is nothing but a number that is precise, means it is definitely going to have a lot of digits, but the thing is it might not be very correct. That means it is giving us a lot of information but says nothing about how correct it is. So that is what you can say here. So coming to the accuracy, so a number which may be an accurate is correct. That means here I am having a pi, so equal to 3.14. So here a pi, a number that is accurate is correct, but it may not have a lot of information inside it. So do I find here any number of bits, many number of bits? No, it is highly impossible for a number if I have asked you what is the accurate value of pi. So you are just going to tell me 3.14 and you are not going to provide me much amount of information. So that is the difference between precision and accuracy. So, so here also when we are having one example, like if tick time scale 1 second by 1 millisecond, if I have asked you a question, so you are going to say me that the accuracy of your I mean your delay, your quantity is 1 second, and the precision of your quantity is 1.001 second. Time precision is 1.001 second. Sorry, it is not the time precision, it is a precise value of your quantity. Okay, so accurate value of your quantity is 1 second, and precise value of your quantity is 1.001 second. So this is how the accuracy and precision involves in your time scale compiler directive. So let me take one example and demonstrate you what exactly the difference and what is the usage in our Verilog HDL programming about timescale. Okay, before it, let me move to my Verilog program here. So what happens here is sometimes I would like to have in my single simulation test bench, better I would like to define two separate modules, and for each module I will be having some separate I can say a compiler directive, a timescale compiler directive different I am taking here. Like you can see here module, my module name is dummy1, and for this dummy1 I am having my compiler directive as tick timescale 100 nanoseconds by 1 nanoseconds. That means the reference of the basic time unit, how much I am maintaining here, it is 100 nanoseconds, and time precision is 1 nanosecond. Okay, let me take some different, some again next module. The next module I am going to define here with dummy2 as its module name, and for which the compiler timescale compiler directive, its values I have changed it. That means the reference time unit for your module 2 is different with the reference time unit with your module 1. Okay, so here like the remaining instructions or the definition of the program of the module is I am having here the alike instructions. I didn't made any difference here. Whatever the definition your module dummy1 is giving, the same definition your module dummy2 is giving. So the functionality of your dummy1 and dummy2 modules are, I am having some variable here, that is mood swing. So the modes are swinging, it is going up, it is going down, like 1 0 1 0, the mode is swinging continuously. So this mode swing variable I have taken with a data type reg. So initially my mode swing is at logic 0. After sometimes so initialization of mode swing is happened. Next let me take one always block such that my modes is continuously swinging for every 5 seconds. 5 seconds, no, now it is not 5 seconds, because I have already told you that I am having the basic time unit, the basic unit of measurement is how much here for a quantity 100 nanoseconds. So here 100 nanoseconds I am having, that means I am having the accurate value for a quantity is 100 nanoseconds, and the precise value of a quantity is 100.1 nanosecond. Okay, I am not going to consider any precise value, let me consider the accurate value for time being. So 100 nanoseconds is the basic time unit of measurement for my delays in my program. So here hash5 is my delay in the program. Hash5 is the delay, means always hash5 mode swing 1 equal to negation mode swing 1. That means for every 500 nanoseconds my mode swinging is going up, going down, going up and going down. So in this manner it is happening. Next end and after some time you will have to finish your simulation or execution of the program. Next, end module. What are the instructions that I have given here for module 1? The same instructions I have also given for module 2, except with my module name change and time scale reference time unit or the unit of measurement change, and my variable change, that is mode swing 2 here I have taken. So remaining every instruction is as alike with my first instruction. So my agenda here is, so in my single simulation test bench program, I have created here two different modules with its timescale compiler directives of different reference time unit values. Okay, so for dummy 2 module, the reference or the unit of measure, basic unit of measurement for the delay is 1 microsecond, and for the dummy one the basic unit of measurement is 100 nanoseconds. So can I say this 100 nanoseconds is nothing but 0.1 microsecond? Yes, because 0.1 microsecond is nothing but 100 nanoseconds, and this is 1 microsecond. Let me simulate this entire code in our Verilog, in our Xilinx tool. Before going to the simulation work, let me have some general observation here. That means 0. For every 0.5 microseconds, mood swing 1 is getting toggled here. That means it is going to logic 0, next after 0.5 seconds it is going to logic 1, logic 0 and logic 1. So that means here in module dummy 2, my mood swing 2 is going to logic 0 and logic 1 for every 5 microseconds. So for every 5 microseconds it is going to logic 0 and logic 1. But coming to here, for every 0.5 microseconds it is going to logic 0 and logic 1. That means, can I have an observation in this manner? Like you can able to see in the PPT slide. So mode swing 1, mode swing 2, here are the two different register variables for two different modules. Just ignore this 10 nanosecond and 100 nanosecond. Okay, so here the reference time unit for your module 1 is 0.1 microsecond, and for the reference time unit for your module 2 is 1 microsecond. Sorry, it is not 1 microsecond. Let me check once again. Yeah, sorry, it is 1 microsecond itself. So that means here, like the mode swing 1 is going to logic 0 and to logic 1, so it is consuming nearly around 0.5 microseconds. So for mode swing 2 to go from logic 0 to logic 1, it is nearly consuming 5 microseconds amount of time. That means, can I say that the mode swing 1 is executing 10 times for each execution of your mode swing 2? You can see here. That means the mode swing 1 is having 10 times its activity for single time activity of your mode swing 2, like 0 1 0 1 0 1 0 1 0 1. How many times activity had been happened? 10 number of times. For 10 number of events is happened for a single occurrence of event in your mode swing 2. So let me go with the simulation work here. Let me copy the program code. Copy and this new source. So in the single test bench only I have instantiated these two different modules with different timescale compiler directives, and let me run the program here. Right. So you can observe deeply in the console window that before observing in the console window, let me check here. Let me come back to the PPT slide. So mood swing one activity is continuously taking up to 50, no, I can say it is 5 microseconds, because the basic unit of measurement for this delay is 0.1 microsecond, and the basic unit of measurement for this delay is, that is in the module 2, it is 1 microsecond. So I cannot say it is 50 microseconds, it is 50 into 0.1 microsecond, that is 5 microsecond, and this is 5 microsecond. So from 0 to 5 microseconds, mood swing one activity or the event is taking 10 times for a single event occurrence in your mood swing 2. So at 5 microseconds, mood swing 1 is coming from logic 1 to logic 0. At 5 microseconds, mood swing 2 is coming from logic 0 to logic 1. Let me check here. One is 1 to 0 and next is 0 to 1. Yeah, at 5, yeah, this is the one. At 50, yeah, this you can observe here. At 50, it is coming to 0, and this one, it is coming to 1. Why, you can ask me a question, sir, it is 5 and why it is 50 means this basic time unit is in terms of 0.1 microsecond, this basic time unit is in terms of 1 microsecond. That is the difference you can able to notice here. So this is about your timescale compiler directive. That's it for the timescale. Let me close the window. Yeah, and the very next one is useful system tasks. So what are the system tasks here? And like for example, these system tasks are mainly useful for they serve the job of file IO functions, like opening and closing of the files, and to write the file, to read the file. These purposes mainly comes under the category of file IO functions. So according to the formal definition of your file IO functions, like they perform operation on files, that's it. Okay, like opening, closing, displaying, writing into the files. So like let me discuss in detail step by step the syntax, the system keyword $f open system task it is. So if I would like to open any file, that means here a file can be opened with system task keyword, that is $f open. So whenever I am using the $f open here in my syntax, you can able to see here. So immediately what happens, the task $f open, it returns a 32-bit value called a multi-channel descriptor, that is MCD. So whenever if $f open is invoked, a MCD file, a 32-bit value that is generally called as an MCD file is being returned. So here $f open I have used here means it is definitely going to return some 32-bit quantity. So this 32-bit quantity should be handled by some file handler. Okay, this file handler we call it is a multi-channel descriptor. Okay, by default only the 08 bit of your multi-channel descriptor, in fact that is bit 0 is always set, which is nothing but a standardized output for your multi-channel descriptor, and sometimes we going to call this bit 0 as channel 0. So whenever I am invoking $f open here, that is each successive call to my $f open, it opens a new channel. So a new channel and returns a 32-bit value to your file handler, which is nothing but your MCD. So like for example, it is my default MCD value. So whenever $f open is invoked, that means what happens in the next stage, channel 1 is set. If once again I have opened $f open, I have used channel 2 is set, next channel 3 is set. In this manner it goes on setting the bits or channels. And coming to here, the 31st bit, it is a reserved quantity, a reserved thing. So similarly, the user here, he can specify only the name of the file as an argument, as a part of the argument. So $f open will open the file, like it may be some abc.v file or ha.v, half adder.v, full adder.v. In this manner we can open the files. So if once the file is open, if I would like to close the file, how to do it? We use $f close as the syntax. Yeah, $f close file handler. Now we are not going to use here file name dot extension like fa.v or ha.v. We are not going to use here. We have to close the opened file. What we are going to close here, not directly file, we are closing the handle, file handler or the multi-channel descriptor, that is file handler we are closing here. So if I don't have any file handler here, okay, so simply I have used $f close without any arguments. That means whatever the files that were open, all will be getting closed. That is the purpose of your $f close here. Let me have an example on this one and we'll come back to writing into the files, how to write into the files. Yeah. So as I have said you that $f open, here I have invoked to open my result.dat file, like some file with some extension here. So whenever $f open is invoked, it is returning a 32-bit value, and this 32-bit value is collected by your file handler, which is of 32-bit quantity. So definitely its data type or its category have to be mentioned before its usage. Here fh is of type integer, that is why I have taken, it is the reason behind taking the fh as an integer. And after that reg a comma b comma c, it is a scalar variables of type registers. So once I have opened the file, so what I am doing here, a equal to b and c. Some person will be giving b value and c value, and he will be assigning me to find out a value. Okay, I have evaluated my a value, and this a value have to kept back into the file, that is result.dat. So how to keep back this a variable value back to the result.dat means I simply use here $f display, that is used mainly for writing into the files. So how to write into the files? There will be one particular format will be there, that is $f display or $f monitor, $f strobe, $f write. These all are the things by which we can able to write into the files. Okay, and the syntax is $f display file handler. That means this through this file handle only we need to write something into the file. So fh is my file handler here, and the what is the result that I have calculated. The result, because it is a scalar quantity, all the three are scalar quantities, so the result is in terms of a binary value, and the result, that is evaluated value, is sent into your file handler, and this file handler will pass the information into your file, that is result.dat. As soon as writing operation have been completed successfully, we can simply close the file, that is $f close fh. So see, if this argument is not there, so I don't have any argument for my $f close. So what your compiler do, whatever the files that were previously open, all will be getting closed here. So this is the purpose of $f close. Okay, and the next one is, yeah, in this manner you can write into the files. Okay, let me have one more example on writing into the files. That is $f display. I have said you that these all are the keywords can be used to write into the files. So here I am having file handlers or the multi-channel descriptors handle1, handle2, handle3 of type integer. Initial, begin, handle1. So $f open invoked once, twice and thrice. Whenever they are invoking, they are definitely going to return some 32-bit value. So first time invocation. So it is opening file1.out, 2.out, 3.out. As soon as they are opening certain files, definitely a 32-bit value will be written, and some variable is waiting to collect this value. So $f open. So channel 1 is set. By default channel 0 is set. Now $f open is invoked once for the first time. That means channel 1 is set here, or bit 1 is set. Next invoking bit 2 will be set, and next invoking bit 3 or channel 3 will be set, and this will be the corresponding hexadecimal value for your file handlers handle1, handle2 and handle3. So we need to remember these three values. Yeah, and next let me create some more file handlers or the MCDs, that is desk1, desk2 and desk3. These are the three file MCDs of type integer, and I am doing certain operation here. So desk1 equal to handle1 or operation, that is bitwise OR. I am doing with logic 1 or simply. So handle1, what is the value of your handle1 in hexadecimal format? I am having here, that is 32-bit hexa 00000002. So do for this value do OR1. So OR1, what will be the result you are going to get? This is the result. So this result your desk1 will be storing. So your desk1 is a multi-channel descriptor, and this MCD or this file handler is related with your file handler, that is handle1. But this handle1, this is the file handler or the MCD, is having a direct relation or a contact with your file1.out. That means your desk1, if I would like to write the evaluated value of your desk1, if I want to write, so I can write simply to I can write into my file, that is file1 out.out. So I cannot write directly, I have to follow some specific format is required, that is $f display, which is highly useful in writing into the files. $f display, next file handler, comma, something display1, some information I am going to write here. So through this multi-channel descriptor, I am writing some information or some data into my file, that is file1.out. Similarly, desk2, this MCD, this multi-channel descriptor is doing some bitwise OR operation between two file handlers, that is handle2 and handle1, where again $f display, that means I need to write the content of my MCD, that is desk2, into a file. Which file? That means here, as soon as desk2 is evaluated by taking the inputs from handle2 and handle1. So handle1 is related with file1.out, handle2 is related with file2.out. That means here desk2 is somewhat the other way is related with file1 as well as file2.out. So I need to write the information, the desk2 MCD value, that is calculated here as this one. This information is written into both of the files, that is file1.out as well as file2.out. And what is the information here I am writing to my file, both the files display to some data, or you, what is the whatever the information, it is your wish, you can write whatever you would like to write. So this is about I mean desk2, the desk2 I mean the desk2 some value is written into file1.out and file2.out. Similarly desk3 is nothing but handle tree. So what is the value of your handle tree here? This much, this is the information. So desk3 equal to handle tree. So I would like this desk3 is equal to handle tree means it is directly related with file tree.out. So if I would like to write something through this MCD or the file handler, through this file handler only, now I am going to access or I am going to write into my file tree.out. So what is the data? It is my wish, some data through my file handler I can write into my file tree.out. Similarly coming here also, through this desk2, that is a file handler, through this file handler I am going to write some data to my files file1.out, file2.out. Why? Because desk2 is related with handle1 and handle2. As handle1 is operated on file1.out and handle2 is operated on file2.out. So through this big handle, the data is passed through the subhandle 2 to your file2.out, and through this big handle the data is, which data, display to data is passed through the big handle first, next subhandle 1, and next to your file1.out. Next here also the data display 1 is passed through your desk1 big handle, I mean to say big multi-channel, I mean first multi-channel descriptor, next to through the handle 1 descriptor, and next to your file1.out. In this way the data is can be written into the files. Okay, so this is a brief discussion on the like file IO functions, that is file input and output functions. And let me discuss about $strobing here. Sorry, dollar strobe, or the terminology here is strobing. So strobing, what is the strobing here? We familiarly know what is the purpose of $display and $monitor system task in the previous or the earlier sessions. Now for the strobing purpose I am using here $strobe as my keyword. So by using $display, sometimes we may face a problem of non-deterministic during the time of execution. So in order to overcome this problem, we replace the $display with $strobe here. So like $strobe is actually, it is very similar with a $display task, but with some slight difference. That is, whenever I am using $strobe in my Verilog program, so it is always executed after all your assignment statements in the same time unit for execution. So here I am having two different always block. You can see here these two always block will start execution at the same time unit, right? So instead of $strobe, if I have kept a dollar display, okay, so dollar display here is there. By mistake or by a chance, A is dependent on B, C is dependent on D. By mistake, I don't know which always block is executed priorly. Of course, they start execution at the 0 simulation time onwards only, but it is always not sure that this only will be executed first and next always block is executed last. It is not such a thing. There is no such a thing here. So sometimes if I have, instead of $strobe, I have kept here dollar display. That means if by mistake this second always block is executed, what happens? Do I be getting displayed with the values of A and C here? No. Why? Because it got executed first than this one. So which makes me in a state of non-deterministic. So in order to overcome this drawback, I simply replace the dollar display with $strobe here. So whenever $strobe is used, it is always executed. That means this always block is executed after the remaining always block or after all other assignment statements in the same time unit. Can I say now, whenever $strobe is there, an asynchronous activity is indirectly generated or happens. So this is the usage of your $strobe keyword. Yeah. Next one is random number generation. So what is the purpose of the random number generation here? So the random numbers where and when they are mainly used here. Like these are generally used for generating a set of test vectors. For example, if I am having ABCD as an inputs, ABCD as an inputs, and these are passed to one design, and I will be having my output, that is Y. So I generally have to pass 16 test vectors, like from 0 0 0 to 1 1 1 1, to verify the functionality of my design and observe how your output Y is responding to my input test vectors. Okay, if the number of test vectors are very high, if the number of inputs are very high, so for 4 inputs I can generate manually my test vectors. Now if the number of inputs are 6, that means 2 power of 6, 64 test vectors I need to generate. If the number of inputs are, for example, 70, 2 power 70, these many number of test vectors, is it possible manually? Definitely no, it is not at all possible manually. So if I would like, that means I want to catch sometimes, like I am not sure that for example, if you can take the 4 inputs you are having in your design and you are having an output, single output, that is Y. What have done is 7 to 8 manually I have given test vectors to verify the functionality of my design. In between I have skipped some test vectors. Okay, so if I skipped some test vectors, the skipped test vector, if I have applied, it may not sometimes give me a correct output. That means, can I say an error have been occurred or an error is present in my design unit, so which is highly avoidable. So for this purpose we are going to random number generation. So as mentioned, these are required for generating a set of test vectors in order to catch the hidden bugs in the design. mainly use it for the performance analysis of chip or performance analysis of your schematic or module or design. We use the keyword that is $random. So here $random can generate the test vectors of signed quantity. And if I have used here a seed as an argument for my $random, here seed actually, to be frank, it is an optional thing. What is the purpose of using the seed here is to ensure the same random number sequence is generated each time the test is run. Okay, so for example, $random of 2, I have some value, whatever you can give. So if $random, if I have taken for my 4 input design, so it may generate in decimal 4, 7, 11, 14, like that. Other, if I have taken like $random with some number inside it, $random of 1 or $random of 5, that means seed is equal to 5, let me keep. So like for every time the test is run, the same random number, like initially if I have $random of 5 is the syntax. For every time the test is run, I am getting here the same random number generated, like 12, 12, 12, 12, 12, 12, 12, any number of times, many a number of times. So that is the purpose of seed here. That is why it is an optional thing here. And coming to seed, it may be of data type, time, register, integer, etc. So let me explain the concept of random number with the help of an example here. Yeah, I am having here something. Yeah, let me take this as an example. Copy it here, saving. This is my test bench. Okay, so you can able to see here, right? I have the test bench module name is test. Here B are some inputs which are of 6-bit quantity. That means 6-bit quantity means 2 power of 6, that is 64. The highest value of A is 63 and the lowest value of A is 0 for A and B. And integer I comma j, some integer I comma j is of type integer, initial begin. For loop I have used it because I am going to generate the value of A and the value of B for 6 number of times. That is why I have taken here for loop. And and similarly I can able to generate the random value of B which ranges from 0 to 63. I may get any value for 6 number of times, 6 number of random numbers, 6 times a random number B is generating here. Okay, so $random of 2, I am just skipping this step for time being, and let me go with this one. So this is, I would like to get an unsigned random number, that means positive random number I would like to have. That is why you need to use curly braces and put $random inside it here also. So A equal to the curly brace, that means it is an unsigned random number I am generating, but I have given certain restriction. That means from 0 to 63 you are restricted to generate up to 0 to 49. That is the restriction I have kept to here. And similarly the restriction that I have kept to generate a random number B is 59. Up to 0 to 59 you can generate your random number. So let me simulate the program and check how I am going to get the output wave outcome in console window, the results. Something somewhere there is a mistake. Yeah, Here you can see. So let me keep this name as TV, that will be better. Okay, what is the mistake I have here? Okay, I didn't copy these two things, ma. Copy. And now it will work. So as I have mentioned you, A 6 times it is generating some random number, and B also 6 times it is generating some random number. So let me observe the result in the console window instead of the waveform window. So this is the result: A 48, 47, 7, 37, 7, 7. Whatever, it is some random number. That is what. And B 6 times it is generating the random number like 5, 22, 21, 49, 18 and 17. So this is the usage of your random number keyword. Okay, so let me see, let me also demonstrate you some good example. That is ripple carry adder, you know it, right? So what is the purpose of ripple carry adder? So 4-bit ripple carry adder, here I am taking my. So I'm mainly focusing on the test bench unit as well as the design unit. So this is my design unit, you can able to see. So 4-bit triple carry adder, inputs are ABC in, outputs are S out and C out. Inputs AB are 3 down to 0. That means it is a 4-bit quantity and C in is a scalar. S out is a 4-bit quantity and C out is again a scalar. So this is the definition for my ripple carry adder. And coming to the test bench, I have used here tick define you are going to call this tick define as a compiler directive. So tick define m $monitor. So whenever what is the purpose of tick define? Whenever m occurred in your program, this is replaced with $monitor. As you can see, m occurred here, so m is replaced with $monitor. So the text macro, the macro name, it is m is a macro name. The text, it is the text of the macro. Text is this one, macro name is m. So module 4-bit triple carry adder registers wise instantiating my design unit inside my test bench unit. So Cin initially have taken as 1-bit binary 0, and for so like I am having here 4-bit triple carry adder. That means A is of 4-bit quantity as well as B is of 4-bit quantity. I can able to get here 16 cross 16, that is 256 different number of combinations for my 4-bit triple carry adder design unit. Am I right or wrong? Yes, obviously. So that is why I am using here for loop. For I equal to 0, I is less than 15, I equal to I plus 1. Okay, for actually I need to keep here 16, that is also good. As I have taken, yeah, that is why I just restricted its limit because I have taken in this manner. Okay, we will check once again. For I equal to 0, I is less than 15, I equal to I plus 1. Even though if you keep here 16 also, I will be getting the code, no worry. So, and for j equal to 0, j is less than 15, j equal to j plus 1. That means, can I have, instead of 15 cross 15, 225 number of test vectors, I can able to generate now. Okay, I mean 225 number of instances I can able to generate now. Okay, So for every instant, I may have A value and B value. For that means A and B are giving their random numbers for 225 number of times here. Okay, but the thing is, I want to keep some restriction here. Like A and B are of quantities 4-bit quantity. So I want to get from 0 to 15 itself only. That is why I have taken percentile C to keep the restriction. That means even though if I don't keep also it is acceptable. So let me keep percentile 16 and b equal to dollar random percentile 16. So after generating random numbers of a and b, wait for 1 second, and after that you can generate the second instance of two random numbers. So these two random numbers are generated, wait for 1 second, and in the next instance again the two random numbers are generated and wait for 1 second. In this way the loop repeats for 225 instances. So initial dollar monitor, of course this is the most familiar instruction, you are very aware of this. Okay, let me check how the dollar random keyword is performing here. Yeah, 0 to 224, 225 I said, right? That means 224 instances you have got here. So let me check some randomly some instance like 50, 34. Where is this 34? Yes, this is the 34. Okay, I need to make certain some modification. Something is missing. Okay. Let me include this program here now. So whenever tick include fab.v, so full adder in behavioral I have written in .v as an extension, and whenever compiler directive I have used it in this manner means I will be generated here in this manner. That means automatic preprocessor or the compiler directives will be a folder is created here under the kit evaluation kit. Here this is FPGA kit. Under the FPGA kit some one folder is created. That folder we call it as a compiler folder, I mean compiler directives folder. Okay, we'll discuss this point later during the time of lab experiments. So let me simulate the program once again. There is a mistake somewhere. Yeah, now I have got the output now. We can check in the console window. So let me take an instance because I have here 225 instances. 26th instance, let me take 26th instance. I have given Cin equal to 0, A equal to 1 and B equal to 8. So what will be A plus B is sum. Sum equal to 9 and carry out equal to 0. Okay, in this manner I can able to get for A and B 225 different instances, and similarly I will be getting for sum out and carry out also 225 different instances, as it directly depends upon A and B inputs. So this is the usage of your $random keyword. Okay, so let me. The next is initializing memory from file. We know how to declare the memories, as we have discussed this thing in data types discussion. There is a special system task here to initialize the memories from a data file, and also to read the numbers maybe in binary or hexadecimal format. So we use here the system key task keywords, that is $read mem and $read mem h. Mem b indicates it is to read in binary format, and mem h it is to read the data in hexadecimal format. So here in the argument or the sensitivity list, you can able to find that file name and memory name, these are compulsory and mandatory, whereas the starting address or the finishing address of your memory is very optional thing. Okay, so like how to read the content from your file or how to read the data from your file, we'll see. I have created here one file. The file name is init.tex. So some extension, that is tex is the extension that I have used here, and the file name I have given the name for my file as init.tex as an extension. So this file contains all the initialization data for my memory file, for my memory. Okay, as you can see here, the addresses are specified in this file with operator, and addresses are generally will be in the hexadecimal number or format. And whereas as you can see here, I am having 8 data: 0th data, first data, second, third, fourth data, fifth data, sixth data and seventh data. That means I am having 8 address locations, and for each and every address location I am having some data. So by seeing this, I can able to say that the data capacity is 1 byte or 8 bits. Now you can also observe or notice here that each and every data is separated with white space. Okay, and what about the uninitialized bits? Generally, the uninitialized locations or the uninitialized bits will be occupied by unknown or X. So this is my init.tex file, and the init.tex file is having some memory content. Okay, now let us see how to access this init.tex file. Okay, and meanwhile I will also show you a program. Yeah, let me open and simulate it first. So through this Xilinx ISC, I am able to do all the simulations which are required for demonstrating you different concepts. So here I have written some Verilog code, and this code is used to access that init.tex file. Okay, so like let me give the name for my Verilog module as test and reg 7 down to 0 memory. As we know how to declare the memories, we have discussed this thing in the previous lectures. And so memory, this is my memory name. The memory name I have given as simply as memory, and this memory is having 8 address locations, and each and every address location is having some 8-bit data content. Okay, so that means I have declared an 8-byte memory that is having 8 address location. Each address location is having 1 byte capacity. Apart from it, I have taken some I as a ransom variable. It is of type integer. Next, initial begin. So what is my what is my main motto here? I need to access that init.ex file. So according to this PPT slide, I have explained you the syntax to if I want to read any data file in memory in binary format or in hexadecimal format. If it is in binary format, I will be using $read mem file name comma memory name. Like the starting address and the finishing address is optional thing here. So I am having here $read mem, and what is the file name? The name of the file is init dot, and the extension I have kept for that is tx, some extension, and comma memory name. What is the memory I have given for my memory unit? What is the name of my memory? Simply I have given memory itself. Okay, $read mem init.exe comma memory. Now for I equal to 0, I is less than 8, I equal to I plus 1. So that means here I am having 8 address location for my memory in init.ex file, and each and every memory location is having some data. So dollar display memory of 0, memory of 1, memory of 2, memory of 3 up to memory of 7. What is the corresponding data that will be displayed in binary format? Why? Because the thing what I have used here, the system task keyword, that is $read mem b. So that is why I need to get the output in binary format. So I ranges from 0 to 7 because I have the memory file, the memory capacity is 8 address locations it is, and each address location is 8-bit width. Okay, and memory of 5, the content of the memory. So end module. So let me simulate the program now. Am I able to produce the same thing? Because this is my memory, right? So this memory is having 8 address locations. Let me, for your understanding purpose, so this is for your understanding, let me make like this. Yeah. Right. So 0th location, first location, second location, third, fourth, fifth, sixth, and seventh. That means 8 address locations are there, and each and every address location is having 8-bit data content. Okay. So let me check whether my program is also producing the same whatever is present in my init.ex. The memory content is same or not it is producing. Let me check. Yes, it is producing the same. So memory of 7 is 5 zeros, 3 ones last. So here 5 zeros and 3 ones. Yes, it is producing, and this is 0 0 0, remaining all x. Memory of 0 is 0 0 0 and remaining all of x. Yeah, it is producing. So in this way we can able to read any file, or we can able to access or read the numbers in binary or hexadecimal format. So this is the initializing memory from a file. Okay, and let me discuss the next thing, that is value change dump file. So what is this value change dump file here is, so like basically the VCD, we generally call this value change dump file as an VCD file, where it is generally an ASCII file that contains information like what is my simulation time, and what is the scope of my module, and like basic signal definitions or signal declarations, and when are the signal values are going to change during the time of simulation. So all this information are written into a file. That file is nothing but value change dump file. Okay, so VCD file we generally call this one. Okay, this VCD file is created only during the time of simulation. So before the simulation we cannot find this VCD file in our folder. Okay, so that means what is the main motto of this VCD file is the designers can dump either the selected signals or all the signals which are present in your module to your VCD file. So for doing all these things we definitely require a system task keyword. Okay, that will provide for selecting any module instance signals to be dumped, or like internals of the module or complete module or submodules, everything. Like we do have here the option what are the signals that have to be dumped into my VCD file. So so for example, if I want my during the time of simulation, if the information have to be dumped into a file, I will be using the syntax that is a $dump file here. So what is the purpose of this $dump file is the simulation information, like at what time the simulation started and what is the scope of my module and what are the signal definitions at what time the signals are varying. All this information is dumped into this some dump file, that is .vcd file. So this .vcd file, for example exp.vcd file. So in this exp.vcd file, directly means I definitely require $dump file in arguments exp.dmp. In this manner I can able to do the dumping process. Let me explain you with a Verilog example for this one, such that the concept will get cleared. Okay, in this folder you can observe here I am just removing VCD files. So here I have already created one VCD file, and this I am deleting. Okay, now are you able to find any file which is having an extension of .vcd? No. So let me open the project. So here I have taken the example of ripple carry counter. This is my design unit, you can able to view. So this is my ripple carry counter design, and let me remove all this bloody stuff. Okay, right, so everything is clear. First thing is I will explain you the program once again. Of course we had came across this program before itself only, but anyhow let me recap for your understanding of VCD concept. So I am having here ripple carry counter program, and this is my design unit. So the inputs are reset and clock, output is Q, output is 63, some otherwise I will take as 15 down to 0. Okay, 15 down to 0 of Q, otherwise 3 down to 0 is enough, because 4-bit ripple carry counter is enough for my experiment. So input clock comma reset, and I am instantiating 4 times T flip-flop modules TFF0 1 2 3. So you know how these sensitivity list signals are arranged. Okay, and after this one TFF Q clock, because 4 times I am instantiating T flip-flop means definitely I need to provide the definition for my T flip-flop module, because from template an object is created. TFF is my template or the module name from which object is created. So that means I need to define, or I need to provide the definition of my T flip-flop module. So module TFF Q comma clock comma reset, output Q, input clock comma reset, wire kit. So inside my T flip-flop, you know how the diagram will be. Like it will be having an inverter along with one D flip-flop. So D flip-flop is instantiated. So this is my template from which an object of D flip-flop has been created. And similarly, one NOT gate I have used here. Hence D flip-flop definition also completed. So the next thing left is module D flip-flop definition. That is Q, D, clock and reset. Q is the output, D, clock and reset are the inputs. I am defining or declaring this program in a behavioral abstraction. So of course output is Q. Definitely Q should be of type reg. Input D comma clock comma reset. Always I need to completely depend on what are the inputs. Passage reset or negate clock. So I am depending on negative edge of a clock activity and passage reset. That means whenever your reset is going high, your output will be 0. Else output will follow input, because it is a non-blocking assignment. Okay, so hence completed the definition of design unit. Now let me open the test bench unit. So in the test bench unit also, module test bench, reg clock, reg reset, wire. Okay, these all are the things we came early only. I'm just removing all the comments here because it is unnecessary to me actually. Right. So inside my test bench, which is a top module, I am instantiating design unit, and the template of the design unit is ripple carry counter, and the object is created, that is R1 name and Q comma clock comma reset. The same order how I have declared during the time of definition, the same I need to maintain here itself also. So initialize clock. So always your clock should toggle. It is a continuous activity. Again, all initial begin. So reset equal to 1 bit binary 1. At simulation time 0, your reset signal is going to 1 bit binary 1. After 15 seconds, reset is going to 0. Again after 180, it is going to 1 bit binary 1. Whenever reset is going to 1 bit binary 1, your output Q will be initialized to 0. Like it may be in any number from 0 to 16, 0 to 15, because it is a triple carry counter, 4-bit triple carry counter case, having outputs Q3, Q2, Q1 and Q0, as you can see here. So the outputs may have a range from 0 to 15. So like the output may be in between any of the number. Whenever your reset is going to 1 bit binary 1, immediately your output is switching to logic 0. So that is the main purpose of reset signal. Again, after 10 seconds, that means 15 plus 180, 195 plus 10, 205. After 205 simulation time, because this is a sequential block, remember this thing. All the statements will be executed after the execution of its preceding statements. That means after 205, your reset is going 1 bit binary 0, and your system or the design activity will be getting resumed. So after 205, 225 dollar finish. So completely stopping the simulation, terminating the simulation, I can say. So dollar monitor is to monitor the outputs, because Q varies from 0 to 15, that is why %d, and initial begin. So my concept is VCD file. So everything, that means simulation information, I can say all these things are nothing but simulation information is to be dumped into a file. That file name, let me keep as dump.vcd, or otherwise dumping or dump2, dump4.vcd or dump1.vcd. Let me give the name as dump1.vcd. So value change dump. What are the values that are changed to your signals? Because here Q is an output signal, right? Its value is changing. for every clock. Okay, for every negative edge of your clock, your value of q is changing. That means your reset value is that means the variables like reset, q, clock, all these variables values are changing, value change and dump. So that is the meaning of it. So that all this information, all the simulation information is dumped in your file, and that file name I have kept as dump1.vcd. So this is the system task I need to use whenever I would like to do the dumping process, $dump file. Okay, after that one you have seen $dump vars. So if I don't have any argument here, I am doing dumping all the signals in the module if no argument is present. That means all the signals in the design unit are dumped. If if $dump vars of one means dumping the variables in the module instance stop in the module instance stop. Okay, so anyhow, so let me simulate the program and show you like what will be the content of this VCD, which is nothing but an ASCII file. Before it, let me cross check. I don't have any dump one here. After the simulation, I'm going to get the dump one. Okay, so let me run the program. So before it, what are the variables here? I'm having clock, reset and q. Okay, reset is changing with certain delay. Okay, with all this information you can able to see in the dump file. Okay, so this is the general output. Anyhow, now open the folder. Yeah, I am having here dump1.vcd. This file is created now. Let me check what are the contents in this file. Okay, these contents in the file will appear once I close the simulation. Let me close the simulation now. Yes, yeah, and again reopen the file. That is dump1.vcd. Yeah, that means dollar date, at what time and at what date I have done the simulation. Thursday, March 18 at 3 o'clock 9 minutes and 20 seconds 2021 end. So for every statement there will be some end here. Okay, so that means like semicolon you can treat. So version, which version of this one simulation I am using here, I mean ISE project navigator is p.49d. that also will be presented here. Version of Xilinx p.490. And okay, that means this is one statement. Good. And p4.49, this is one statement. After it, end. So this statement is mentioning date, and this statement is mentioning version, end, and this statement is mentioning me time scale. So time scale means, again check, 1 picosecond. Yeah, precision time scale. And coming to here, yeah, it is also 1 picosecond precision time unit, right? And end scope. So what is the scope here? Module db. Scope, this is my main scope here. Yeah, this is module db is the scope now, right? End. Next is variables. What are all the variables we are having here in the test bench scope? q3, q2, q1, q0, as well as clock and reset. So q3, q2, q1, q0 are of type wires, right? And so after completing, definitely is one a kind of semicolon or dollar end in terms of ASCII file. It is, as it is a VCD file which is an ASCII file. So dollar end for each statement, dollar end, and dollar end. So for q of 3 I am going to use this as a representation, and for q of 2 this as the representation, q of 1 this is the representation, and q of 0 this will be the representation. And next inputs are clock and reset. For clock I am going to use this one as a representation, and reset this is the representation, and because this is of type reg. So dollar up scope and end. So I completed all the scope, what are the things present inside the scope. Now at 0, dump vars. So all the variables, all like a dump, all I am doing here, all the signals in the module I am dumping in the .vcd file. So at simulation time 0, that is 0 0 0 0. So dollar indicates q of 0, hash q of 1. Okay, this is exclamatory indicates q of 3, this one indicates q of 2, and percentile indicates clock and indicates reset. In this manner it happens. Okay, so dollar end after 5000. Why 5000 here? Let me check. That means after 5000, because 5, this is 1 nanosecond and this is p1 picosecond. The difference will be in 10 power of 3. Okay, minus 3. Okay, so the time difference into will be multiplied. That means here hash 5 is there. Hash 5 means I will be getting here hash 5000. That means precise value I am taking here, because here 1 picosecond, 1 nanosecond by 1 picosecond was there. So nanosecond was the accurate value and picosecond will be the precise value. So in terms of so can I say 5000 picoseconds? This is because everything I am mentioning in terms of a picoseconds, but in the program it is 5 nanoseconds. Here 5 nanoseconds means 5000 picoseconds. So in this way 5000 picoseconds, after it 10,000 picoseconds, 15,000 picoseconds, 20,000 picoseconds. What are all the things changing that will be mentioned here? That means clock will become 1, here clock will become 0, here clock will become 1, because percentile symbol is used for clock. Next, after 30 seconds clock will be 0, after 35 seconds clock will be 1. Clock is a continuous activity. So during the time of clock continuous activity, what are the changes, what are the remaining signals, are they changing or not? So the remaining signals are mentioned by these things. So effectively, correspondingly the symbols will be coming into 0 1 0 1 state, like dollar. You can see here also percentile, dollar, all these things. Once if you investigate the VCD file, every activity that the simulation is undergoing, I mean that is the test bench unit is undergoing during the time of simulation, all the signal and its values, what are all are changing, everything can be found in your dump file, that is your VCD file, that is value change dump file. Okay, so this is about that means you can also observe here at 220 seconds or 220 nanoseconds in the program, and here it is 220,000 picoseconds, it is 220,000 picoseconds. Okay, that means 220 nanoseconds. So that means these all are the signal values changed. Okay, and the simulation definitely got stopped here at 225. That is why no more information. Okay, in this way the dollar dump file can be used to dump the simulation information. Okay, so this VCD file is nothing but generally it is an ASCII file which contains a simulation time, scope, all the variables of the signal definitions, and when and where the signal values are changing during the time of simulation. So this is the usage of your dump file, dollar dump file. Okay, so that's it for today's discussion. Thank you.